Hi, in this lecture I'll be talking about orthogonality, unit vectors, and orthonormality and how they're related. This goes with chapter 2.6 of the deep learning textbook that this course is accompanied with, so I highly encourage you to read 2.6 after watching this lecture. Okay, so we're going to start off with unit vectors and then see how that leads us to a discussion on orthogonality and orthonormality. So basically the definition of a unit vector is a vector with the norm of 1. So when you take a norm of a unit vector, it's equal to 1. So let's take an example of something that isn't a unit vector, so 3, 4. So let's take the Euclidean norm of this, and you'll usually be talking about the Euclidean norm because it's very easy to understand geometrically, as we'll see in a second. So let's take the Euclidean norm of this. So we basically square each of the things, or of the elements, and then we take the square root of that, so we get 9 plus 16, which is square root of 25, which is equal to 5. So the norm of this vector is 5. And we can geometrically understand this pretty nicely. When I first kind of introduced norms, I used the Pythagorean theorem as kind of a way to segue into a discussion of it. Say if we have some vector like this, with a x component of 3, like this one, and a y component of 4. So that's basically this is the same vector. If we have a vector like this, we can understand it to kind of be mapping a right triangle in the Cartesian plane. And the hypotenuse of this right triangle is the magnitude, or the length of the hypotenuse of this is the magnitude of the vector, because the vector kind of is the hypotenuse. So we'll see here that, of course, we measured the magnitude of the vectors. So the length of this vector is 5, and this creates a 3, 4, 5 triangle here. All right. But if we're looking at this and we want to see how do we turn this into a unit vector, so how do we take this and manipulate the terms inside of it so that when you take the norm of this modified vector, we get 1? Well, let's go back to here. So basically we want to try to modify this triangle so that the hypotenuse is equal to 1, because that's the magnitude of the thing. The length of the hypotenuse is equal to 1. Well, but we still want to keep it so that the direction of the vector is the same. We don't want to alter the direction of the vector. We're just talking about magnitude. So we kind of want to scale down this entire triangle in a way. But what do we want to scale it by? Well, if we divide it by 5, if we divide all sides by 5, it'll still be the exact same shape. But if we divide all sides by 5, this will become 1. So the length, the magnitude of the vector will become 1, which is a good sign. Then we have 4 over 5 and 3 over 5. So this is essentially just creating a little triangle. If we kind of keep this like it was for 3 and 5, this is essentially just creating a little triangle here with a hypotenuse 1, this 3 over 5, and 4 over 5. We're just kind of scaling down the entire vector but preserving its length. And that's basically what you're doing when you're turning a normal vector into a unit vector, is you're keeping its direction but changing its magnitude. So let's see what happens. So we divided all sides by 1 over 5. So this new vector, it has the x component 3 over 5, y component 4 over 5. So basically just multiply this old vector by 1 over 5. So let's see what the norm of this is, and hopefully it's 1. So we multiply this by 1 over 5. So this basically just gives a 3 over 5 and 4 over 5. So let's take the norm of this, the Euclidean norm again. So 3 over 5 squared plus 4 over 5 squared is equal to 9 over 25 plus 16 over 25. So it's 9 plus 16 over 25, which is equal to 25 over 25, which is square root of 1 equals 1. So we checked here that our intuition was correct, and now the unit, I'm just checking if my microphone isn't dead yet, but it's dying. So we checked that our intuition was right, and by scaling down this entire kind of triangle, by the norm of the vector, the kind of old norm of the vector, we were able to get to a unit vector. So basically what we did was we just multiplied this old vector element-wise by 1 over the old norm. So in general, if you wanted to turn some vector x1, x2, all the way to xn into a unit vector, we would just multiply each term by 1 over the norm of that vector. Okay, hopefully that makes sense. All right, so let's get rid of all this. Oh, and one more thing I just want to mention about unit vectors that'll come in handy. It might seem a little random now, but when we take a dot product, well, let's just kind of start with an example. So say we have v transpose, we have a vector v, and let's say v is a unit vector. So if we do v transpose v, so we dot product it with itself, we get 1. always, if v is a unit vector. And let's do a single example just to kind of, hopefully kind of convince you that this is true without proving it. So say we have the same vector we had before, so 3 over 5, 4 over 5, which you know is a unit vector now. And let's dot it with itself, so let's put this transpose right next to it. So now we're going to be multiplying this and this, so that'd be equal to 9 over 25, and then adding that to 4 over 5 times 4 over 5, which is going to be 16 over 25, adding those, and that equals 25 over 25 equals 1. And you can see why that's kind of true about how we first scaled that vector to make it a unit vector. You can see why that makes it so that when you kind of dot product this vector with itself, you get a similar thing, because you can essentially think of dotting a vector with itself as kind of squaring each of the terms. You're multiplying it by kind of itself. So you can think of it as squaring the terms again, and of course, since that's kind of the way you made the unit vector, you're going to get a similar answer. So whenever you are dotting a unit vector with itself, you get 1, and that'll come in handy later down the road. Okay, so now let's talk about orthogonality, and this might seem a little random compared to unit vectors, but it'll come together when we talk about orthonormality. But let's talk about orthogonality first. So essentially orthogonality is just a funny way to say perpendicular. Like if you have two vectors like this, that there's a right angle between them, you'd often call these perpendicular, but we like to call them orthogonal, often because when you have multiple dimensions, so it's a bad arrow, so you have multiple arrows in space, so in 3D space we have 3, and they're all orthogonal to each other, so they all have right angles between each other. Then you can say that this set of 3 vectors is orthogonal to one another. One thing to kind of notice is that the maximum amount of orthogonal vectors is the same as the space you're in, the same as the dimensionality is the space you're in. So say you're in 2D space, so we call this R2 space, or 2 space. If we plot 2 vectors here, we can have an orthogonal pair of vectors. But as you can see, there's no way we can have a triplet of orthogonal vectors. You can't have some 3 vectors that are all orthogonal to each other. And I think you can quickly realize that that's pretty much impossible, or is impossible. But say we upgrade to 3-dimensional space, or R3 space. So say we have this, right? So now we can have some vector here, and some vector here. You can kind of imagine them as going along the coordinate axes. So we have a right angle between all of these, and a right angle between those two. So in 3 space, you can have a maximum of 3 orthogonal vectors to each other, but of course you can't have 4 orthogonal vectors. So that's just a nice thing to note, and it's helpful to know. But how can we actually mathematically tell if I keep checking this if it's alive, yes it is. But how can we actually mathematically tell if 2 vectors are orthogonal when we just get the vectors as kind of listed numbers in a way? Well, if we have v and w, we can tell if they're orthogonal simply if v transpose w, or the dot product between them, is 0, or the other way around. It's still the same thing. So if that's true, w, v are orthogonal to each other. Great. So that's kind of the important thing to note. The reason for this is a bit complicated, but you can intuitively kind of think of a dot product as a measure of how close the directions of 2 vectors are. So say we have a pair of vectors here. You can see that they're almost pointing in the same direction, so their dot product is going to be very high. If you have something like this, so they're pointing in basically the most opposite direction you can think. Note that if we start going this way, we kind of start pointing along this axis anyway, so we kind of start pointing in the reverse direction of this, so we're going to get negative dot products. But this is kind of the most different of a direction you can point in without going into the negatives. And you can kind of understand then why, when we have 2 perpendicular vectors, or orthogonal vectors, that the dot product between these 2 is 0. Because once you start going like this, then you start getting a negative dot product, and if you start going like this, you get a positive dot product. Okay, so that's kind of why, I guess, somewhat very quick intuition. Not a great intuition, but hopefully it satisfies you. But yeah, so if we can check by dotting two vectors v and w to check if they're orthogonal. So we can give an example, I guess, here. A very kind of basic example would be the coordinate axes in 2D space. So say we have this vector here and this vector here. So say this is 1, 0, so it goes 1 along the x and 0 along the y, and this is 0, 1. So these obviously should be perpendicular or orthogonal, and we can check if that intuition stands. So if we have our 1, 0, we dot this with our 0, 1, this 0 times 1 is 0, 1 times 0 is 0, 0 plus 0 is equal to 0. So, it stands there. We can take a little bit more of a complex example, maybe, and I won't draw this out because it might be a little too much. Maybe I'll try. But say we have a three-dimensional vector, say 3, 3, and then let's take these two vectors. So 3, 1, and then let's say we have negative 1, and then 3, and then we have 0, and then 4. So let's say we take those two vectors. So these, I won't draw them out, or we can maybe try to draw them out. I'll try my best. Let's see. So we say we have this kind of coordinate axes here. Let's say this is the x, this is the y, this is the z, and then this is kind of 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So let's try drawing this first vector here. So that's 3 along the x, minus 1 along the y, so that's kind of here, and then 0 along the z, so that's kind of going to here, I guess. So that's the 3, negative 1, 0. And then now let's take the second vector, so that's 1 along the x, and then 3 along the y, and then 4 upwards, so that's going to be about here. It's going to be kind of pointing like that. So I think you can kind of see geometrically how these are right-angled to each other, right? They kind of stand in a plane to one another, and they're kind of right-angled there. So that's kind of the geometric intuition, but let's see if this stands. So let's dot these. So I won't write it out in transpose notation. So 3 times 1 plus minus 1 times 3, so that's going to be minus 3, plus 0 times 4 equals 0. So that's going to be 3 minus 3 is 0, plus 0 is, so the dot product between those is 0, and we can see geometrically that they are perpendicular to each other somewhat. Okay, so hopefully that makes sense. Hopefully that makes sense. But really where these come in handy is when we start creating orthogonal matrices. But the first thing we have to introduce is the concept of orthonormality, which is basically just a kind of love child of these two subjects of unit vectors and orthogonality. So basically two vectors v and w are orthonormal, so that's different than orthogonal. V and w are orthonormal if v transpose w equals 0, so if they are orthogonal, but also if v and w are both unit vectors. So there's two requirements for a pair of vectors or 3 vectors or 4 vectors to be orthonormal to each other. It means that all those vectors have to be orthogonal to each other, so pointing in perpendicular directions, but they all have to be unit vectors. Okay, also a kind of good example, a very boring example, but a good example nonetheless is, again, 1, 0, and 0, 1. Because each of these have a length of 1 and they're perpendicular to each other. So those two are two orthonormal, a pair of orthonormal vectors. And again, you can think of like maybe 1, 0, 0, 0, 1, 0, and 0, 0, 1 as being a triplet of orthonormal vectors. So basically just very simply kind of 1 along this direction, 1 along this direction, 1 along this direction. But remember that you can have a lot more complex ones. I just don't want to go through the time of going through another example, but you can have triplets of orthonormal vectors in any direction as long as they're all the same length and as long as they're all unit vectors. But the reason why orthonormality is such an important concept is something when we get to orthogonal matrices. So let's talk about orthogonal matrices. And it's kind of confusing that they're called orthogonal matrices. They really should be called orthonormal matrices. But say we have some matrix here. And let's make it 3 by 3. Some square matrix. So say we make each of the rows in this matrix. We make each of the rows in this matrix a vector. So let's say, well, first of all, let's start with some v1, v2, and v3. And let's say v1, v2, v3, I don't know where I wrote it twice, are all orthonormal. So these all point in perpendicular directions and they all have a unit length. So say we make v1 the first row of this matrix, v2 the second row of this matrix, and v3 the third row of this matrix. And let's call this matrix Q. Now let's transpose this matrix and multiply with it, and you'll see where I'm going with it after a bit of time. So let's say v1, so let's transpose this, so v1 gets here, and then v2 gets here, and then v3 gets here, right? So that's Q transpose. Now let's multiply these, and we don't actually have to have numbers in there to multiply them because we can use the rules that I talked about. That might have seemed kind of random, but maybe makes sense now. So since v1, v2, and v3 are orthogonal to each other, well, orthonormal really, because each of these are unit vectors. Since they're unit vectors, when we take the dot product between v1 and v1, we get 1, right? Because when I just talked about when we have some unit vector v and we transpose it with itself, we get 1. And that's exactly what we're doing here. We're doing v1 and v1, and they're both unit vectors, and they're the same. So we're going to get 1 here for our first element. Now we do v1 with v2. And remember, when we have two orthogonal vectors and we take the dot product of them, we get 0. And since v1, v2, and v3 are all orthogonal to each other, like to be clear, v1 transpose v2 equals 0, v1 transpose v3 equals 0, and v2 transpose v3 equals 0, right? All of these are orthogonal to each other. So when you do v1 with v2 and we dot it, we get 0 here. Similarly, if we do v1 with v3, we also get 0 here. Now let's go into the next row, and you might see what's coming now. So now we do v2 with v1, we get another 0, because those are orthogonal. Now we do v2 with v2, and now we're kind of dotting it. We're kind of dotting with itself again, so v2 and v2 equals 1. And v2 and v3 equals 0, and then we can kind of guess that v3, v1, and v3, v2 are both 0, so. But then we do v3 and v3, and we get another 1. So you can see that when you multiply an orthogonal matrix, and surprisingly we call them orthogonal, even the columns are orthonormal, this wouldn't be true if the columns were just orthogonal, they have to be orthonormal to each other, but when the columns of Q when the rows and columns of Q, and I'll explain that shortly, when the rows or columns of Q are orthonormal to each other, and you multiply it by its transpose, you get the identity vector here. Identity matrix, sorry. But when I talked about how the inverses of a matrix are unique, so if you have some matrix A, there's only one inverse for it. But since Q multiplied with Q transpose is equal to I, that means Q transpose must be equal to Q inverse. Right? So that's kind of the really big thing about orthogonal matrices, is that their inverse is their transpose. And that's really huge because inverses are very, very computationally expensive to calculate, but when we have an orthogonal matrix, we can just transpose it and get its identity. And I mentioned here as we make v1 the rows of it, but it turns out if you make v1 the columns, and then you multiply its transpose, so we have some q, and then you have the q transpose before it, it still equals I. I just took this as kind of an easier example because we can do this dot product intuition, but both this and this equals I, so it doesn't really matter which order you do it in. But the thing is that simply its inverse of an orthogonal matrix is its transpose, and that's really big because this doesn't come up all the time when we're doing other things. In the next lesson on eigendecomposition, we're going to be talking about this, but this is just really big because from now on we're going to always be trying to make our matrices. When we're doing matrix equations, we're always going to be trying to make them orthogonal matrices, because whenever we want to inverse it, so say we have our ax equals b situation and we want to solve for x, we multiply both sides by the inverse, and we immediately have the answers for x, right? But we have to do this ugly inverse term. But if A was Q, if A was an orthogonal matrix, then we would simply have to do Q transpose here. And that's so much easier to calculate. It's a pinch. It's super easy. You can do it in a pinch. So that's really the thing I want to get from this, is that the importance of orthogonal matrices and kind of the concepts that we need to know to understand orthogonal matrices. So I'll see you in the next lecture. Bye.